Hello, good morning, everyone. So let us start the day today. So today, the first talk is by Tarraneh. She will be talking to us about the FRB local environment and host galaxies. Over to you, Tarraneh.
Okay, great. So thank you so much. First off, I do want to thank the organizers for having me. I'm really sorry that I wasn't able to be there in person, but I'm very thankful that I still have the opportunity to talk to everyone today. And specifically, I want to talk about FRB host galaxies and what they can teach us about their progenitors. And I believe you all had an entire day last week dedicated to some of the more hands-on analysis of FRB hosts and how we analyze optical data. And so I think some of what you hear today might be a little familiar, but I'm really hoping to provide a little bit of a broader context for why host galaxies are so important when it comes to understanding FRB progenitors. And some of you may have seen this figure from me before, but this is really just to emphasize that this is true not just for FRBs, of course, but astrophysical transients in general. So this is something that has a long history in the field of transients. And at a very fundamental level, the idea is that we can look at the global properties of the galaxies where these different types of transients are coming from in order to understand what types of stars live in those galaxies. And then by extension, if we know the stellar populations in those galaxies, we can start to understand the different types of progenitors that could form these different classes of transients, right? So on the left-hand side here, I'm showing various classes of transient phenomena. And on the right, I'm showing the progenitor systems that produce these different transients as a function of their age. And the way to really think about this is really, again, in terms of the ages of the stellar progenitors and how that's reflected in their host demographics, right? Or the different types of galaxies that they live in. And so the youngest, most massive progenitors are tracing these ultra star-forming galaxies. And then as you move further along in age, so systems that are not necessarily tracing star formation, right? If your progenitor's insensitive to how quickly you're forming stars, for instance, then you start to probe more quiescent galaxy environments. And an example there is these progenitors involving white dwarf systems, where the white dwarfs form at very late times, long after the star itself has formed, right? So when it comes to the global host properties for FRBs, I'd say that there's been a fair bit of progress in the field in really just the last few years as we've started to localize more and more events. The current sample of FRB hosts includes about 120 or so published events, so we're really building up this very nice sample. But at the same time, these represent a very small fraction of the total FRB population. So despite the fact that we have many thousands of FRB detections to date, just about 3% of these have localizations that are small enough where we can identify a host. And I think as part of the school last week, one of the things that was covered was host galaxy associations and how we do this probabilistically. And the fact that you really need a precise enough localization to associate the FRB with a galaxy. But really the key result that has come out of this sample of localized events so far is that there's a very wide diversity in host types. So ranging from these very low luminosity dwarf galaxies in a few cases to massive spiral galaxies and even a few quiescent galaxies. And so if we go back to this figure with all the different transient classes and how their progenitors connect back to their hosts, what we're seeing is kind of a mix of star-forming and quiescent galaxies. And so ultimately, we want to reconcile this diversity in host environments with FRB progenitors. Okay, but what can we take away from the current sample of host galaxies so far? Well, I'd say that the general consensus based on sort of the first few studies of host demographics is that their host galaxies, or at least their bulk properties, seem to be consistent with a population of magnetars formed through core collapse supernovae. So you can see in the top right figure here how FRB hosts sort of trace the star-forming main sequence of galaxies, shown as these black points. So with really a wide range of stellar masses and star formation rates. And then similarly, when we look at a BPT diagram on the top left here, so this is showing the dominant source of ionization within these galaxies, whether that's coming primarily from ongoing star formation or AGN. And what we find for FRBs is that most hosts fall in the star-forming locus, with just a few showing evidence for AGN or liner emission. And then for a few FRBs with milli-arcsecond precision localizations, we're even able to see that they're co-located with regions of active star formation within their hosts. And I'll talk a bit more about that later. But the general kind of picture here is that this is all broadly consistent with core collapse supernovae progenitors. And then, of course, we had a kind of a smoking gun back in 2020 with this very exciting discovery, which kind of definitively connected at least some subset of FRBs to magnetars, or one FRB, I should say. So this was the discovery of an FRB-like event from a known galactic magnetar. And initially, the first bursts that were detected were actually a couple orders of magnitude below the faintest detected FRBs in terms of their luminosity. And so I think there were a lot of questions about, is this really an FRB? Does it just represent kind of the tail end of the FRB luminosity function? Perhaps we don't detect such bursts at extragalactic distances because they're too faint, and so on. But you can see that a number of repeat bursts were detected with really a wide range of luminosities here, kind of comparable to what we see from cosmological FRBs. But nevertheless, this really was the first kind of definitive evidence linking at least one FRB to a magnetar. So more recently, Asaf Horowitz and Ben Margalit did a really nice analysis where they take into account the multivariate nature of host galaxy properties. So things like a galaxy's star formation rate and stellar mass are not independent of one another. And so when we look at these different distributions to compare to say field galaxies or other types of transients, we want to make sure we're not marginalizing over any one parameter, right? We want to make sure that any framework takes into account the fact that these properties are interconnected. So these plots here are showing the mass-weighted and star formation-weighted distributions of galaxies at a fixed redshift. And you can see that FRBs trace neither one of these distributions exclusively, but instead what they find is that they trace a combination of both stellar mass and star formation. And so right away, this tells us that FRBs cannot be exclusively associated with young neutron stars born from core collapse supernovae, which we would expect if they just trace star formation. And instead, this dependence is more in line from what we observe for type 1a supernovae. And in fact, one of the theories put forth for FRBs is the accretion-induced collapse of a white dwarf. And it turns out that's not inconsistent with the overall host demographics, especially when we kind of take this multivariate nature into account. Okay, so this is, again, a lot of what's been done when it comes to FRB hosts, especially their global properties. But that being said, if we come back to this diagram, there are multiple classes of transients that might emerge from what globally appear to be the same types of stellar populations, right? So for example, we see a number of different types of transients originating in star-forming galaxies. And so the question becomes, how can we differentiate between these classes in order to really understand their formation channels? And to contextualize that a little bit, I want to spend a little bit of time highlighting some of the things that have been done in the literature for other types of transients. So beyond just this connection to star formation, historically, galaxy metallicity has played a big role in transient host studies. The figure on the left here is showing galaxy metallicity as a function of stellar mass for a few different types of transients. And one of the things we see is that the hosts of long gamma ray bursts and superluminous supernovae tend to exhibit much lower metallicities than what you'd expect from the generic kind of mass metallicity relation for galaxies, which is shown as these lines up here. So for some reason, these transients really require very high angular, they exhibit this preference for very low metallicity environments. And what we think is happening here is that they require very high angular momentum. And the higher the metallicity abundance, the more angular momentum you can actually lose through stellar winds, for example. So just one example of how metallicity can play a role in transient progenitor formation. For tidal disruption events, so these are stars that are ripped apart by the galaxy's central supermassive black hole, we find an overabundance in these so-called bomber-strong galaxies, where you see strong bomber emission. And so you can see in the spectra here how the bomber series lines are very heavily absorbed. And these types of galaxies have often had recent galaxy-galaxy mergers. So this could lead to perturbed stellar orbits, so stars more likely to fall within the lost cone of a black hole, or you might wind up with a higher concentration of stars towards the galaxy center, right? So these are just kind of two nice examples of how we can incorporate galaxy properties beyond just star formation to learn about transient progenitors. Okay, zooming in on the more local environments, there's a lot we can learn by studying the more immediate environments around transients, and specifically how they kind of compare to the rest of their host galaxy. So coming back to superluminous supernovae and long gamma ray bursts, when we look at their hosts, they have very similar host demographics, right? Just kind of bulk host properties. And we think that both are associated with rare explosions of massive stars. But it turns out that if we look at the locations of these transients within their host galaxies, there are some key differences that help us start to distinguish between the properties of their massive star progenitors. So this is a really nice paper led by Brian Su and collaborators, where they use high-resolution HST observations to see how the locations of superluminous supernovae compare to the rest of their host galaxies. And what they find is that superluminous supernovae actually occur in some of the dimmest regions of their host galaxies. This is actually in contrast to what's seen for long GRBs, which reside in very bright UV regions. And so right away, this provides some distinguishing power between their central engines, right? This is telling us something about their massive star progenitors. And in particular, what they discuss in the paper is that this might indicate somewhat less massive, older progenitors for superluminous supernovae relative to long GRBs. Or perhaps the progenitors in some kind of disrupted binary system where it gains a velocity kick and is kicked out of a star-forming region. But the point to really emphasize here is that while the global host demographics for both long GRBs and superluminous supernovae are quite similar, when we zoom into the more local environments around these sources, there are some key differences that can help us differentiate between their possible progenitors. And I'll come back to a few cases where that's really been relevant for FRBs a bit later as well. So there has been some nice work exploring the host light distributions for FRBs using HST observations. This was a study led by Alexandra Mannings using high-resolution HST observations to look at the immediate environments around a sample of 8 FRBs. And what you can see from these really nice HST images is that the locations of the FRBs are coincident with the spiral arms of their host galaxies. But when you look at the fractional flux values, shown as these figures on the bottom here, so in other words, how bright is the position of the FRB compared to the rest of the host, what we see is that FRBs don't occur in the brightest regions of their host galaxies. And you can think of UV and IR as proxies for star formation and stellar mass, respectively. And so this is giving us insight into both the level of star formation and stellar mass at the FRB location. In other words, these FRBs don't seem to trace the youngest, most massive stars. And another thing I'll just point out here very quickly is that the locations of FRBs in their hosts are distinct from those of short gamma ray bursts, which tend to occur in the faintest regions of their host galaxies owing to their very large kicks. So that being said, this is of course based on a relatively small sample size, and that's why you see these gray error regions extending as wide as they do. And so ideally, we want to build up a much larger sample of FRBs with very high resolution imaging so we can start to cut down on the uncertainties here and really understand how the distribution of FRBs with their host galaxy light compares to other types of transients. So this is again kind of highlighting that knowing that an FRB is located in a spiral arm really isn't enough. We know that stars are forming in these spiral arms, but knowing where within the spiral arm the transient occurs actually offers some additional discriminating power. So these types of studies have been carried out for supernovae, for example, looking at how different classes of supernovae are distributed within spiral arms. And what they found is that type 1bc supernovae tend to occur closer to the leading edges of the spiral arms compared to type 2 and 1a supernovae. And so this is telling us that the progenitors of type 1bcs are likely younger and more massive. We've seen this type of analysis applied to an FRB. This is a non-repeating FRB discovered and localized by Kraft. And in this case, the authors use a combination of high-resolution optical observations and linear resonance theory for spiral arms to place a limit on the age of the source. So they find an age of about 21 megayears, which is not at odds with a young magnetar scenario. I won't go into the details here, but it is a really nice analysis, and I encourage everyone to check it out if you haven't already. But this is really the direction that we want to move in with FRBs and being able to do this with a much larger sample of events. There's a lot we can do with high-resolution radio observations as well. The idea here being that radio observations are a good probe of dust-obscured star formation in galaxies. So this is work led by Vic Dong, a graduate student at Northwestern, looking at the host galaxy of a hyperactive repeating FRB that was discovered by CHIME. And this is one of a handful of FRB hosts where we do detect radio emission due to star formation within the host galaxy. So you can see the VLA radio images up top from 6 gigahertz, where we can start to resolve the emission down to 1.5 gigahertz. And because these are high resolution observations using the most extended array configuration of the VLA, we can actually map that star formation across the galaxy. And this is an example where if we were to just look in the optical, we don't see any obvious star forming regions at the FRB position. So in the bottom there, you're seeing HST images of the host. But when we look in the radio, we find that that star formation emission actually does extend to the location of the FRB. And so the conclusion that we can draw is that the FRB progenitor likely did form within this star forming region. Another thing that's been increasingly explored for FRBs as we kind of build up a nice sample of nearby events is their H1 content and distribution. And the idea here is that neutral hydrogen gas in a galaxy typically extends well beyond the distribution of stellar light. So you can see that from the red contours here. And so by studying H1 and FRB hosts, we can search for evidence of galaxy interactions in the form of tidal tails or filaments, where these would hint at recent triggered star formation and hence short delay times for FRB progenitors, right? So some association again with star formation. Again, this is something that's also been looked at in the context of other classes of transients. Really a common theme here is when we talk about host galaxy studies for FRBs, we're really building on a rich legacy of the same type of studies for other transients. So these two examples are for long GRB hosts. And what's interesting here is that we see a deficit of H2 relative to neutral hydrogen. So at face value, this is a bit strange because H2 or molecular gas is thought to be the main fuel for star formation. And we don't really see it in large abundances in these long GRB hosts where we know there's ongoing star formation. But the fact that we see a lot of H1 is telling us that there is some connection between neutral hydrogen and star formation. And in this case, the prevailing idea is that the galaxies are accreting metal-poor gas from the IGM, which in turn triggers star formation. And if you recall from earlier in the talk, this is consistent with the fact that long GRBs are typically found within metal-poor regions of their host galaxies. So again, a really nice example of how you can kind of bring these host observations across the electromagnetic spectrum together. So for FRB hosts, there have been H1 observations for 5 galaxies so far, 6 if you include the Milky Way. And what's really interesting that's come out of this initial sample is that all of these FRB hosts show evidence for recent galaxy mergers or interaction events. And that's based on the observed asymmetry in the H1 profile. So here's an example in the bottom left of what those line profiles look like. And then in the top right, if we compare the level of asymmetry that's observed for FRB hosts to GRBs as well as field galaxies, there's maybe a hint that the hosts of FRBs tend to exhibit somewhat more asymmetric lines relative to GRBs and regular galaxies. But of course, the sample size is really small in both cases, so kind of hard to say definitively one way or the other. For R3, so on the top left here, this is one of the closest FRBs at a distance of 150 megaparsecs. And if we look at H1 total intensity maps, you can actually see that at the red star there's this compression of the H1 emission right at the FRB location. And in fact, they infer a high H1 column density close to the FRB position. And so again, this is at face value pointing towards a massive star progenitor formed during a merger event. And then because R3 is so precisely localized to milliarc second precision, we can also zoom way in on this particular event to study its immediate environment. And in this case, that very precise localization actually reveals that the FRB is offset by about 250 parsecs from the nearest star-forming region. And this is consistent with what we'd expect for high-mass X-ray binaries. And interestingly, R3 is also the FRB with a 16-day periodicity in its burst activity rate. And so this is not at odds with some kind of binary interpretation. But again, you can see why this combination of very precise FRB localization with high resolution imaging can be a really powerful discriminant for progenitor models. And this is also a good example of why we should be careful about over-interpreting the global host properties. So if we consider just the bulk host properties for for R3, we might conclude a magnetar progenitor in a typical star-forming galaxy, right? But when we zoom way in on its local environment, we see that it's really not that simple. Another really good example of that is FRB 2020-0120E. So this is localized to the nearby M81 galaxy. This is a fairly typical grand design spiral galaxy. But when you zoom way in on milliarc second scales, you can see that the FRB is actually coming from a globular cluster in M81. So globular clusters are, of course, much older stellar systems where we don't necessarily expect to find young magnetars formed through supernovae. But instead, we need to invoke these delayed channels, like neutron star mergers or the accretion-induced collapse of a white dwarf. So again, this is just another example where we want to be careful about what we infer based on the global host properties. So FRB, that FRB is the only FRB that's been localized to a globular cluster so far, but we are starting to see some more evidence for a possible subset of events coming from globular clusters. So this FRB here is another hyperactive repeating FRB that was localized to a massive elliptical galaxy by the CHIME outriggers. The fact that it's a quiescent elliptical is already a bit unusual relative to other FRB hosts. In the bottom right here, I'm plotting the specific star formation rate as a function of age of the galaxy. And you can see that the host is really an outlier compared to other FRB hosts. And the other really interesting thing is the large offset between the host and the FRB itself. So the figure on the left here is showing its offset compared to other FRBs from the literature. And what we find is that it's offset by about 40 kiloparsecs, which is the largest observed for any FRB to date. The only one that really comes close is the M81 FRB in a globular cluster. And we can also compare to the distributions of offsets for globular clusters in a few elliptical galaxies. So those are those light blue lines here. And again, you can see that the observed offset is also consistent with the typical offsets observed for globular clusters in elliptical galaxies. So maybe some compelling evidence for a globular cluster origin, and something we really hope to constrain with JWST in the future. So finally, I just want to mention a recent result from the CHIME collaboration that really highlights the utility of very precise FRB localizations. This is an exceptionally bright, non-repeating FRB that was localized to a nearby NGC galaxy at a distance of 40 megaparsecs. And because it was localized with the full CHIME outrigger array, so this gives you a maximum baseline of about 3,500 kilometers, the projected physical resolution corresponds to only 13 parsecs. And so you can see from this really nice MMT image that we can zoom way in on the local environment of the FRB and actually see that it's slightly offset from this nearby star forming region. And because it's so close and it has such a precise localization, it also makes it a really great target for follow-up with space-based telescopes to conduct high-resolution imaging of the local environment. And here I'm showing images of the field obtained with JWST. So you can see in the bottom left panel where there's actually a very faint source that appears near the center of the FRB localization. So in this case, given how faint it is, we might be seeing something like a red giant star or a very massive main sequence star. Or alternatively, this could actually be transient emission from what's called a dust echo. So essentially, you have some event that leads to a lot of mass ejection or an afterglow. And then when that the afterglow emission is reprocessed by dust, you get this dust echo. And in this scenario, you actually expect the infrared source to fade on a timescale of about a year or so. And so this is something that we can uniquely test. Okay, so I think I'm nearly out of time, so I'll go ahead and wrap up. Hopefully I've conveyed just how important the host galaxies and environments around FRBs are when it comes to understanding their progenitors. And in particular, how these superlative outliers and local environments offer really strong constraining power for FRB progenitor scenarios. And I also just want to caution that folks don't overinterpret global host properties without very precise localizations. And with that, I'm happy to take questions. Thank you so much.
Thanks for a very nice talk. Yeah, questions? Yes, please.
Hi there. Thanks for your nice talk. I was just wondering, you were telling about the radio continuum observations to understand the obscure star formation, right? Instead of doing that, why can't you go to like mid IR or far IR, in which the dust is more susceptible to these regions, to obtain the proper dust attenuation of each FRB host galaxy to see whether the so-called star formation is changing?
Yeah, you absolutely can. I think radio is kind of a neat way to do this. You can get very high angular resolution observations. And in some ways, it might be a little bit cheaper telescope-wise to do the study. But mid-IR and IR is also a way that one could probe this.
Okay, thank you.
Yeah. Next one.
Yeah, thanks for that great talk. I was curious to know about that H1 detections. How do you quantify the asymmetry in it? And where is that uncertainty coming from, which you showed in the plots?
Yeah, I cannot comment on how they quantified the asymmetry. I'm not too familiar exactly what they did in their analysis, so I would certainly recommend checking out the paper. I don't know if it's just a flux ratio that they looked at. I think the uncertainty that they are, oh no, this is per event. Yeah, I was going to say, I think the uncertainty for the cumulative sample is takes into account the uncertainty on the asymmetry for the bulk sample, and that's why it's kind of difficult to compare to the different distributions because it consists of only a handful of measurements. But I honestly don't know exactly how they quantify the asymmetry. So I'm happy to share the resource, or you can check out the paper for more details.
Okay, thanks. That works.
Yeah, nice talk. So in these H1 detections, the peak in the column density that you're talking about, that is I mean, the H1 cloud itself is like a kiloparsec level structure, right? So what exactly, like you can say that, okay, it's like a high star forming region, but the FRB is extremely like a localized object, right? So and in this H1 detection itself, it just seems like the entire cloud is not properly resolved because of the noise and whatever. So can you comment on this?
Yeah, so you're saying the measurement on the H1 column density is not resolved at the level of the FRB localization?
I mean, it
Effectively.
is not completely resolved. I'm just saying, just the entire galactic region is not. And anyway, the cloud itself is a kiloparsec structure, right? And the FRB is like whatever the compact object. So how can you draw a conclusion based on this?
Oh, yeah. So I think broadly the interpretation is, you know, you're inferring the column density for a kind of a bulk star forming region as opposed to like a particular associating it with the particular star or stellar object that the FRB is coming from. So I think you're right because it is somewhat different scales physically. But it is still a useful measurement in the fact that you can kind of comment on the more kind of local environment, just not the single object that it's coming from, if that makes sense.
Yeah, okay, sure.
Maybe we can go to the last question.
So thanks, very nice talk. You did mention the topic of galaxy orientation, and there have been a couple of works on this in the literature. So I was wondering, what is its observational status? How many galaxies can we really infer the orientation of? And is it indeed the case that there is a lack of edge-on galaxies? What are the correlations, if any, that are seen between orientation and scattering or inferred DM of the host to the extent that we can say that?
Yeah, so I know that Lachlan Marnock with the Craft collaboration is actively working on this. I cannot comment to the status or latest of the results. If Sunil is in the room, he might be more familiar with kind of the latest on that analysis, so I will defer to him. I think he is there.
Thanks.
But yeah, I don't know the latest.
Thanks. We'll just check if there is any question from the online participants. I don't see any hands up, but please unmute yourself and ask if you have any question. Okay. So it seems, yeah, this was a very engaging talk. I myself have few questions, but in the interest of time, maybe we'll proceed to the next talk. Thank you again for the very nice